this session is Alfred Bovon. He's going to talk about SO9, supergravity, and matrix model holography. I'll give you a 5-minute warning.
Okay. Okay. Hi, hello, everybody. I'm Alfred Bovon, coming from Lyon, France. First, I want to thank the organizer for having me. And I would like to just make a comment about the fact I'm not talking about spindle. So I'm sorry about that, because that's the thing. So I'm not talking about spindle, but I will talk about SO9 supergravity and how I will apply that to find new solutions and compute some holographic correlators with that. First, I will start with a small introduction, and then I will show you some new solution that we computed with my two advisors in Lyon, Henning Sampleben and Dimitrios Tsimpis, in a paper to be published, I hope soon. And the generalization that we can have to any breaking of SO9 into some SOP times SOQ. I will come to that later. And then I will show you how to compute correlators with that and what we can have with those correlators. Sorry. Okay. So this talk is in the context of matrix model holography. So, and more specifically in the context of BFSS matrix model. So that was proposed in '97 by the Banks, Fischler, Schenker, and Susskind. 96? Sorry about that. Okay. Sorry about that. So the idea is that we want to have some non-perturbative formulation of the M theory in terms of matrices, and that would help reducing the computations to matrices computations. It can arise in few different manners, but first it could arise at the one-line theory of a large number of D0 branes in some type 2A string theory. And I will focus on this one because I will talk about D0 branes in my talk later on. So to introduce those D0 branes, I'm sure you all know about that, but still, the D branes are a class of extended objects upon which open strings can end, and the D means standing from directed boundary conditions. Here we'll talk about the D0 branes because they are classified by their spatial dimension and the D0 brane being a single point. We can focus on the distribution of those D0 branes to interpret our solutions in the matrix model holography. But the second ingredient that we'll use is the consistent truncation story. And it's another powerful tool that I will use in my presentation to simplify complex theories in our fields. It involves neglecting some of the infinite numbers of modes coming from dimensional reduction, focusing only on a finite number of those lower dimensional fields. It preserves key features of the theory, for example, simplifying the bulk gravity theory in ADS space, but preserving the description in the CFT. In this presentation, I will use a U1 to the 4 consistent truncation of the full SO9 gauge group of my type 2A string theory, and supergravity, sorry, and I will use that to compute correlation function in a matrix model using operators. This truncation was first described by Annabelle Ortiz and Sampleben a bit more than 10 years ago now, but more recently a collaboration worked on consistent Kaluza-Klein truncation and on 2D supergravities with the full truncation and uplift on that. This collaboration by Bossart, Ciceri, Inverso, and Kleinschmidt published 3 papers a bit recently, and I will come to that later on to have more perspective on my work. Okay, so my model, what I'm working on with my advisors. So we are working with 2D maximally supersymmetric SO9 supergravity, and we describe the fluctuation around an S8 compactification of type 2A. So more in the details, what I have in my theory, I have a dilaton that I will call rho, and 128 scalar fields coming from that truncation. But, and 128 scalar fields that are transforming under SO9 as a group of 44 and 84, according to group theory. But here I will use some U1 to the 4 consistent truncation to reduce the 128 scalars to only 8 that are in 2 different groups, the dilaton fields and the accent fields phi A. In this talk, I will put the phi equal to 0 to simplify a bit the thing, but I will come to that later on the perspective. So we can come up with a Lagrangian in this theory, so with a potential term, kinetic term, and the classic Ricci term. And the variable that I will use the more is those XA that are equivalent to the US there, and those are the scalar fields of my theory that I will excite. Yeah, sorry. It's very cool. And okay, so I will focus on some solution that has a particular symmetry inside of this SO9. It's an SO6 times SO3. What I mean about that is that I want to have a domain-wall solution preserving SO6 times SO3 inside my SO9 symmetry. So to that, I will excite my four scalars, x, with some very simple ansatz, just being exponential of a scalar variable small x that will be the main variable in this talk. To see the SO6 times SO3 symmetry, I will embed my truncation into some SO9 matrix, SO9 theory, and parameterize the coset space in an SL9 matrix, and you see that over there, we have two blocks, a 6 by 6 and a 3 by 3. So this preserves, we see that it manifestly preserves the SO6 times SO3 at this point of the SO9. The Lagrangian I showed you earlier can become here very much simpler with only one kinetic and one potential term, only depending on x and rho. After that, I can impose some supersymmetry using some Skilling-Spinner equation. I will not show you the details, of course, to obtain some solution on rho and some metric with f and g being functions of x that are similar to the rho function. Since this x variable is non-vanishing in the bulk, this deformation effectively breaks SO9 down to SO6 times SO3, so in 2 dimensions we have our solution. But that's not what we definitely want, because we want to have the full solution in 11D to interpret it next. So to do that, I need to use some uplift ansatz. So as I said, I use first the one that was produced 11 years ago by Annabelle Ortiz and Sam Kleben, that consists in 2 steps. First, an uplift to the 10-dimensional metric, and then some straightforward Kaluza-Klein uplift to 11 dimensions. So I will not show you the details because that's quite not the point of this talk, but I will come at the end with an enable dimension to a metric that are multiple ingredients inside it. So we have like coordinates, but here I will emphasize the fact that we are 2 spheres that are with radius R3 and R6. So those 2 spheres will remind us that we are working inside this SO6 times SO3 symmetry. And you see this term over there with the H function, depending on those R3 and R6 coordinates. This H function is very complex. I'm not showing it to you, but it remarkably satisfies the Laplace equation. That's why we call the PP waveform solution. Sorry, what? Yeah. Sorry.
It must be a well-known solution.
Yeah, but this H function is modifying everything. Like over there, introducing like.
It's a particular harmonic function that comes out of the object. In general harmonic function with the solution here.
Yes, but I mean the solution is given by the answer plus the harmonic equation.
Right.
That's what we know since just to understand.
Okay, so I will try to focus on this H, and the thing is I want to interpret this function. So the thing is, if you develop this H around one of the 2 coordinates, for example here I can develop it around the R3 coordinate, we can interpret this as the distribution of those D0 branes with some SO6, SO3 symmetry. So this means that we have D0 branes localized at R3 is equal to 0, so at a 0 point of the 3 of the 9 transverse dimensions, but with the distribution in a range in 6. This is some solution that was developed 10 years ago by my advisors and one former PhD. And the question that was asked, when I started my PhD, is that this SO6 times SO3 solution, it's only one geometry, one particular symmetry. Could we extend it? Could we generalize it to any of those breaking to obtain, for example, new deformation, new solution, new symmetries, and sometimes, if possible, new distribution of those branes? That's what I did effectively. So I want to generalize this as SOP times SOQ with any PAQ, of course, adding to 9. So first I will take P as an even number, but that's not a huge fact. This in a paper to be published soon enough. So still, I want to excite those 4 scalars x using some simple ansatz depending on the variable small x. Again, I can embed this into a matrix that has a p by p and a q by q block. So I have my symmetry that is manifest, SOP times SOQ. I can do the uplift and back to this similar metric in 11 dimensions compared to the one I showed you before, with again this H that is satisfying the Laplace equation, so a PP waveform solution. Okay, so I have many more solutions in 2 dimensions now, and their uplift to 11 dimensions. So those solutions are the form of PP wave, not depending on the values of P and Q, and we can interpret them as the distribution of branes. I will show you that. And holographically, the dual of those solutions is a matrix model deformation that breaks SO9 into SOP and SOQ. And what's interesting is that in the matter of the distribution of branes, we have a whole spectrum of those distributions, like whole half integer powers of 1 over 1 minus 1 of the radius squared. So we have any number of those brane distributions that we want, and with different geometry. Those distributions, we could compare it to some article published by Friedman in 2000, like 99 and 2000, where they did some D3 branes distribution in ADS5S5. And we were able to correct this one using their solutions. Shortly, because I have not a lot of time remaining, I will flash you some results about holographic correlators. I remind you that the 128 scalars in our theory splits it in 2 groups, the 44 and the 84. I will focus on about this 44, but we did this fluctuation work for the all scalars in our theory. So they split into a different sector according to group theory. So we have a singlet and 3 fluctuations that we can capture. So 2 of them, we can capture them into our UN to the 4th location by exciting our 4 scalars differently to have some fluctuation of our theory. Then we can use the holographic normalization technique to try to compute the correlators. So we have to change a bit the variable of our system and to put some fluctuation with the background and a fluctuation that we expand in a series of this new variable R, which is basically the X of before. And we come up with some expansions in this new variable. And by imposing the equation of motion, we can select the 3 parameters that are 3 coefficients that are left after imposing the equation of motion. For example, in this fluctuation, this would be the 2nd and the 5th coefficient. Then we want to write the 2-point function as a ratio of those 3 coefficients, the Fourier transform of those 3 coefficients. And by solving numerically the equation of motion, we can try to compute this ratio and then numerically approaching the correlators. We know that from literature that this ratio is supposed to be q to the 6th fixed for the case I'm showing you right now. So we can see that we have our 3 perturbations in this SO6 times SO3 solution having some correlators that we can compute numerically with a very good agreement with this computation theoretical value of q to the 6th fifth. Also, we can compare this result to some Monte Carlo work that has been done by Sekino, I think, in the early 2010, and this also is a very good agreement with what they have. Okay, I will just flash some conclusion and perspective to be on time. So we found the new solutions of SO9 supergravity in 2D and their uplift to 11D. So now we were able to generalize some work that my advisors did 10 years ago to obtain any breaking of SO9 into some SOP times SOQ symmetry. With those new solutions, we were able to uplift it in 11D, see that they are still in the PP wave form solutions, and interpret as distribution of branes having a whole spectrum of distribution of branes. We then were able to compute new correlators by fluctuating the scalar both in the 44 sectors and the 84 sectors, having comparison with literature, very good agreements, and also some to compute some scalar fluctuations that were done before in literature and some that were not done numerically. And some perspective that I could be working on in the next future is to finish the generalization of all the computation of correlators in the new solution, also all the SOP times SOQ solutions, and then to compare our work, for example, with other 2D gravity models using, for example, the result from JT gravity, or using the new truncation ansatz that I talked about in my introduction that may enable us to put new scalars in our theory, for example, in the axiom sector that I neglected in my presentation, having a full theory and one that I could work on with the new uplift and truncation ansatz. Sorry. So thank you for listening to me, and I'm happy to take questions and talk about that.
Questions?
Can I take that? I think.
Have you found the black hole solution in the SO3 times SO6 case?
Sorry. Myself, I did not look for black hole solutions, but I'm not sure we can find out, but the first idea that why they chose this SO6 times SO3, that choice, you might think it's random, not any like 7-2 or something, is they wanted to compare it with some DMN work, more specially. And so that's why they chose this one, but I did not look for a particular black hole solution inside of it.
Another question, what is the dilaton in the SO3 times SO6? Is it this rho variable? So it diverges as x goes to 0, right? Maybe you can go to the expression.
Yeah, sorry.
So you have strong coupling in the deep interior?
Let me think about that quickly. So the dilaton is, yeah, it's vanishing when rho is coming to 0, yeah. I did not look the stroke coupling about that, but
Yeah,
that
fine.
might be an interesting question, yeah.
It typically happens, it's fine.
Okay.
I just wanted to ask about these two-point functions that you computed.
Yep.
So you coded a deformed matrix model,
Yep.
but what I think is happening is that you're giving vevs, so you're not deforming the theory, you're studying non-trivial states in the theory.
Yes.
Do you agree with what I'm saying? Or?
Yes.
So you're not deforming the matrix model, you're computing a two-point function in a non-trivial state.
Okay.
Do you agree with this? Or?
Yes, I think.
So in the vacuum state, this would be a four-point function of two heavy, if you wish, operators and two light operators. So it seems like you're computing much more than you're giving yourself credit for.
Okay.
Thanks.
Yeah, Vasco?
I guess a question out of curiosity, what is your hopes to relate this to like JT gravity? I mean, like obviously it's not the same and should not be. It is much cooler. So like what do you like?
Yeah,
what do you envision doing like in your like last slide?
Yeah, I said JT gravity, but I'm not thinking about JT gravity like pure the JT gravity. I already tried to look at that, and of course it's not the same because mine is more complicated than JT. But I think that it's of an interest to look with other 2D gravity models because a lot of work has been done in 2D, and using this, like this paper I took here. Those papers are very general, talking about 2D models, and they are not focusing on our truncation, and so they are very general. So they open of working in the same framework of other work done in 2D. So I'm hoping that by translating my work into their framework and translating some other work maybe into this framework, we could compare some 2D gravity model, and that's what I was interested about, and not specifically JT, because a lot have been done on JT, and I'm not wanting to do that. But more like comparison of our results with in a bigger framework of the whole consistent truncation in 2D, for example.
Sorry, can I ask one? Since you have this, do you know if there are ADS2 solutions of this more general? I'm sorry that
Actually, so you see there is 2 papers there. The second paper is kind of using their technique for our case, like applying this to SO6 times SO3 and concluding that they can find the same kind of same kind of solution and result that the one I was showing you about with the same consistent truncation at Lipton and Enza.
Yeah, but I'm just asking if there is an ADS2 critical point in the potential here. No.
I have nothing pertinent to say about that. Sorry, and we need to work more on that.
Anyone has looked at that?
Maybe there isn't. I can't answer that.
More questions? If not, let's take our speaker again.